We've already seen that distributions can be characterized by certain functions, such as the cumulative distribution function and the probability mass or density function. We introduce here another function which characterizes the distribution when it exists. It need not always be defined, but when it is, it provides a powerful tool, for example, for computing means, variances, and higher moments, or to prove certain asymptotic results, i.e. results about limits of sequences of random variables. Here is the definition. The moment generating function of a random variable x is defined to be a function of t, and it is the expectation of e to the power t times x. Now, the moment generating function of a random variable may not exist for all t. For example, it may be the case that the moment generating function evaluated at t is infinite for some value of t. But if it is finite, at least for some t in an open interval about 0, then we say that x is MGF good. What's so important about t is equal to 0? Well, successive derivatives evaluated at 0 yield successive moments. In other words, the nth moment of x, i.e. the expectation of x to the power n, is simply the nth derivative of the moment generating function evaluated at 0. To see this, for example, let's consider the first derivative. That is the derivative of the expectation of e to the tx. If we take the derivative operator inside the expectation operator, then the derivative of e to the tx with respect to t is x times e to the tx. If we now evaluate this at t is equal to 0, we simply get the expectation of x. And so the moment generating function evaluated at 0 is just the expectation of x. Now, if we differentiate the moment generating function again, i.e. we take its second derivative, then we will differentiate this expression here with respect to t. And that means we will get x squared times e to the tx. And if t is equal to 0, we'll end up with the expectation of x squared. Now, since derivatives are limits, it follows that in order for the derivatives of the moment generating function to exist at t is equal to 0, we require that x is MGF good. In other words, that the moment generating function is defined on some interval about 0. The point here is that the derivative of a function f evaluated at a is the limit as x goes to a of this quotient here. And for this derivative to exist, it is a necessary, but not sufficient, condition that f of x is defined for all values of x near a, i.e. for all values of x in an open interval about a. And so the derivatives of the moment generating function at 0 can only exist if the moment generating function is defined on an open interval about 0. Now, it should be obvious that if two random variables have the same distribution, then they will have the same moment generating functions. The converse is also true, but we will not prove it here. If two MGF good random variables have the same moment generating function, then they have the same distribution. In that sense, the moment generating function completely characterizes the distribution. Here's another useful proposition. X and y are independent random variables, even only if the moment generating function of their sum factorizes as a product of their moment generating functions. That's an if and only if. One of these directions is hard and we will not prove it here. The other is straightforward. Suppose that x and y are independent random variables. Then of course also e to the tx and e to the ty are independent. Hence the moment generating function of x plus y, evaluated at t, by definition is just the expectation of e to the tx plus y. This factors as e to the tx times e to the ty. And since these two random variables are independent, the expectation of the product is equal to the product of the expectations, i.e. the product of the two moment generating functions. Let's now compute the moment generating function of some of the common distributions that we have considered. Firstly, the Bernoulli MGF. If x is Bernoulli with parameter p, then it takes just the values 1 and 0 with probabilities p and 1 minus p respectively, and hence the moment generating function evaluated at t is just the expectation of e to the t times x, and that reduces to p times e to the t plus 1 minus p. Let's next consider the binomial MGF. If x is binomial with parameters n and p, then it can be decomposed as a sum of n many independent Bernoulli p random variables. Since the moment generating function of a sum of independent random variables is just the product of their moment generating functions, and since we've just computed their moment generating functions, we see that the moment generating function of a Bernoulli random variable with parameters n and p is given as follows. The Poisson MGF is also straightforward to compute. If x is Poisson with rate parameter lambda, then the moment generating function evaluated at t can be expressed as follows using the probability mass function. And if we combine e to the tk with lambda to the k, that can be written as follows. In the infinite series, we recognize the Taylor series for e to the lambda e to the t. And thus the moment generating function evaluated at t is e to the minus lambda times e to the lambda e to the t, which reduces to the following. The exponential MGF is not defined for all values of t. If x is exponential with parameter lambda, then the moment generating function evaluated at t is given by this integral using the probability density function in this case. And this integral is easily computed as follows. Now, if t is greater than lambda, then when we evaluate this at x equals infinity, we get infinity. On the other hand, if t is strictly less than lambda, then when we evaluate this exponential at x is equal to infinity, we will get 0. Hence, the moment generating function of the exponential lambda distribution is only defined for t strictly less than lambda and is then easily seen to be lambda over lambda minus t. Nevertheless, the exponential distribution is still MGF good because lambda is strictly positive. The moment generating function of the uniform distribution is also easily computed. If x is uniform on the unit interval from 0 to 1, then its moment generating function is simply e to the t minus 1 over t, as you can verify yourself by a simple computation. However, notice that this is undefined at t is equal to 0, and therefore the uniform distribution is not MGF good. For our purposes, the moment generating function of the normal distribution is very important. Suppose that x is normally distributed with parameters mu and sigma. We will then show that its moment generating function is given by e to the mu t plus half sigma squared t squared. To see this, first simplify and assume that x is standard normal. The moment generating function is then defined as follows, which can be expressed as the following integral using the probability density function of the standard normal distribution. By completing this square, we obtain the following result, and the integrand of this integral is simply the PDF of the normal distribution with parameters t and 1. Since the integral over all space of any probability density function equals 1, this integral is equal to 1. And hence the standard normal distribution has a moment generating function e to the half t squared. Now, if y is normal with mean mu and variance sigma squared, then when we standardize y, in other words, if we define x to be y minus mu over sigma, then x will be standard normal with mean 0 and variance 1. It therefore follows that the moment generating function of y is defined as follows. Now y is mu plus sigma x. We can take out the factor of e to the mu t. We end up with the expectation of e to the t sigma x. This expectation is just the moment generating function of x evaluated at t sigma. Since x is standard normal, its moment generating function is given by this, except that t is now replaced by t times sigma. And therefore the moment generating function of y is given by e to the mu t times e to the half t squared sigma squared, as was stated above. Next, we consider some applications of the moment generating function. The first two examples show how the moment generating function can be used to compute means, variances, and higher moments. Suppose first that x is normal with parameters mu and sigma squared. We've just seen that the moment generating function is given as follows. Now, if we differentiate the moment generating function twice, the first derivative with respect to t is this, which if we evaluate it at t is equal to 0 is just equal to mu. And hence the expectation of x is equal to mu. If we differentiate this expression again with respect to t to get the second derivative, we obtain the following. And if we evaluate that at t is equal to 0, we obtain the second moment, and that will be mu squared plus sigma squared. Now the variance is the second moment minus the square of the first moment, in other words mu squared plus sigma squared minus mu squared, and therefore sigma squared. So here we have obtained the mean and the variance of a normally distributed random variable without having to calculate any complicated integrals. They follow straightforwardly via differentiation of the moment generating function. We can do the same thing with a Poisson lambda random variable x. Here we saw that the moment generating function is given as follows. Differentiating this expression with respect to t yields the following, as you can easily verify yourself. And if we evaluate that at t is equal to 0, we obtain that the expectation of x is just equal to lambda. You can show that the second derivative is given as follows, so that the second moment is lambda plus lambda squared, and hence the variance is the second moment minus the first moment squared, and that will be lambda as well. So both the mean and the variance of the Poisson lambda distribution are equal to lambda. Now for a different type of application. Suppose that x and y are independent normally distributed random variables. By linearity, the mean of the sum will be the sum of the means, and since x and y are independent, the variance of the sum is the sum of the variances. In addition, however, we can now show that x plus y is also normally distributed. To see this, since x and y are independent, we know that the moment generating function of the sum splits as a product of moment generating functions. We've computed the moment generating functions of normally distributed random variables as follows, which simplifies to the following expression. Now this is the moment generating function of a normally distributed random variable with mean mu x plus mu y and variance sigma x squared plus sigma y squared. Since the random variable x plus y has the same moment generating function as a normally distributed random variable, it is itself normally distributed. As an exercise, you can use the same technique to show that if x and y are independent Poisson distributed random variables, then x plus y is also Poisson distributed, and the rate of the sum is the sum of the rates. We can also generalize the notion of moment generating functions to situations where we consider more than one random variable, in other words, a random vector. If x is a random vector with n components, then its moment generating function is a function of n variables and defined as follows. In other words, it's just the expectation of e to the t dot x, where this dot denotes the dot product. In that case, we have the following proposition, which also generalizes to more than two random variables. Two MGF good random variables x1 and x2 are independent if and only if the joint moment generating function factors. In other words, if and only if the joint moment generating function, which is a function of two variables t1 and t2, factors as a product of the moment generating function of the first variable evaluated at t1 times the second variable evaluated at t2. To prove this, suppose first that x1 and x2 are independent. In that case, the moment generating function is defined as follows. Now the random variables e to the t1 x1 and e to the t2 x2 are independent because x1 and x2 are independent, and hence the expectation of the product is just the product of the expectations, i.e. the product of the moment generating functions. That's the easy direction. The other direction is slightly more subtle. Suppose that x1 and x2 have a joint moment generating function that factors as a product, as above. Now take two random variables y1 and y2 which are independent and moreover such that x1 and y1 have the same distribution and such that x2 and y2 have the same distribution. In that case, by assumption, the joint moment generating function of x1 and x2 factors. But because x1 has the same distribution as y1, the moment generating function of x1 is the same as the moment generating function of y1. The same is true for x2 and y2. Now, because y1 and y2 are independent, we know that their joint moment generating function splits. We've just shown this above. It therefore follows that the joint moment generating function of x1 and x2 is the same as the joint moment generating function of y1 and y2. Now it is a fact that two random vectors which have the same moment generating function will have the same distribution. In other words, the random vectors x1 and x2 and y1 and y2 have the same joint distribution. Since y1 and y2 are independent, and since independence is a distributional property, x1 and x2 are independent also.